Hello, my dear. Let's start our lecture number 8 on hypersonic dynamics. And the topic of today's lecture is hypersonic inviscid flow field, exact missile. So, as you remember, aeronautical history was made on 27 March 2004 when the X-43 Hyper-X test vehicle, which shown in this slide, achieved sustained flight for 11 seconds at Mach 6.9, powered by a supersonic combustion ramjet engine. In this case, it has a special name as a scramjet. This was the first time that an air-breathing scramjet engine had successfully powered a vehicle for sustained flight in the atmosphere. On November 16, another scramjet-powered X-43 achieved sustained flight at nearly Mach 10, making it the fastest airplane in history to date. A street view of this unmanned vehicle is shown in this slide. The vehicle is about 12 feet in length. A photograph of the X-43 resting on supports in the laboratory is given on this slide. Imagine that you are given the job of calculating the flow field and aerodynamic characteristics of X-43 in hypersonic flight. The approximate method discussed in the preceding module would be good for back of the envelope calculation and for gaining insight helpful during the preliminary conceptual stages of design. But the X-43 is designed right on the margin of its required performance, and absolutely the best accuracy is required when calculating its detailed aerodynamics. The approximate techniques discussed earlier are simply not good enough for this purpose. Part of obtaining the best accuracy is to use the full continuity, momentum, and energy equation for fluid flow with no geometric simplification, right? If you are satisfied at first with the assumption of an inviscid non-chemically reacting flow, then these equations are the ones you want to use. But the only way to solve these exact equations, especially for the geometry of the X-43, is numerical. That is what this lecture is all about, exact methods for calculating hypersonic inviscid flow field. Exact means that the full conservation equations have been used with no geometric simplification. In turn, all the exact methods are numerical methods. They must be. So this lecture deals with a sequence of numerical methods for calculating inviscid hypersonic flow. In many respects, for the calculations of hypersonic flows, this is where the rubber hits the road. When you finish this lecture, you will be much closer to the calculation of the hypersonic flow over a vehicle such as the X-43, as you can see in this slide. That is what is exciting about this lecture. And now let's start with the first subtopics, general thoughts. Previous two lectures covered material that is in the realm of classical hypersonic aerodynamics. That is theoretical analysis developed in the 1950s and 1960s before the widespread use of the high-speed digital computer. Indeed, before the age of the computer, there was no other recourse. For the analysis on inviscid hypersonic flows, the exact nonlinear Euler equations on this slide do not yield closed-form theoretical results of a general nature, and hence various physical approximations had to be applied to these exact equations in order to obtain a system of approximate equations which more tractable to theoretical analysis. For hypersonic flow, even these approximate governing equations are still nonlinear. But as we have seen in the last two lectures, various approximate methods have been successfully developed to obtain useful solutions. The point here is that such solutions are indeed approximate, either because the governing equations themselves are reduced to simpler form because of the approximations about the physics of the flow, like small perturbations, or during the course of solution of the exact equations, various limited cases are taken. For example, when we have very high Mach number. This is why the last two lectures was subtitled Approximate Methods. However, even though such methods are classical, keep in mind that the results are frequently very practical and useful. And indeed, many of these classical methods are used extensively today in the engineering analysis of hypersonic flow. In contrast, the present module is subtitled Exact Method. This requires some definition. Here, we deal with the exact governing Euler equation for inviscid flow without any subsequent reductions of these equations based on physical approximation, right? Because we are using the full equation, as you see on this slide, without any approximation. And because there are the exact equations for inviscid flow over all parts of the flight spectrum from subsonic to hypersonic. Okay? We will label the subsequent solution of this equation as namely exact. Okay? So this is a slight misnomer. However, because all the exact solutions are numerical, and any numerical solution is subject to numerical error. For example, we will see that the exact governing partial differential equations can be replaced by finite difference equations. These difference equations are numerically and theoretically different than the original partial differential equation because of the truncation error that is always present in the finite difference formulation. Moreover, during the numerical solution of these different equations, computer round-off errors are incurred. And finally, there is sometimes a lack of preciseness brought about by the numerical treatment of boundary conditions. So, strictly speaking, even numerical solutions are not truly exact solutions of the governing equation. However, with this slight proviso in mind, we will proceed to label such numerical solutions as exact solutions because they begin with the exact governing equation. Stated slightly differently, once we choose to work with the full Euler equation, then the only type of solution with any generality must be numerical. And hence, the term exact solution on numerical solutions are used here synonymously. In more modern terms, this, our module, deals with the applications of computational fluid dynamics, CFD, to envisage hypersonic flow. And this lecture could not have been written 40 years ago. Indeed, CFD is a newly emerging dimension in fluid dynamics, which now complements the more classical dimensions of pure experiment and pure theory. Applications of CFD are impacting aerodynamic research and development across the entire flight spectrum, from subsonic to hypersonic speed. The impact of CFD is particularly strong on hypersonic aerodynamics because the availability of hypersonic wind tunnels and other hypersonic ground test facilities is severely limited, both regarding number of facilities as well as the practical flight range of Mach number, Reynolds number, and temperature levels attainable in such facilities. So thus, in the modern world of hypersonic, CFD serves as a powerful tool for research, development, and design. In this lecture, there is no intent to give a detailed presentation of the fundamentals of CFD. Such an endeavor justifies a book on that subject alone. There are many studies. But on the other hand, to understand and appreciate some of the inviscid flow calculations discussed during our lecture, some of the general ideas and methodology of CFD must be understood. Okay? The assumption is made here that the listener or all my students has not had formal education or experience in CFD. And therefore, as the case demands, we will present various details of the computational technique in a fashion that will be reasonably self-contained. Okay? As a final introductory note, advances in CFD now make possible the envisaged three-dimensional unsteady flow field solution over complete flight vehicle configuration. And moreover, there are a variety of different computational techniques, ranging from the method of characteristics, which is in reality, and all the classical techniques, now made very practical by high-speed digital computers, to finite volume and finite element method. So, in our lecture, only a representative selection of solutions and solution procedures will be given. The choice is based on our experience and bias. Usually, 10 different authors would most likely make 10 different choices, all justified in their own way, and as a result, however, would be the same. That is the absolute appreciation that the Euler equations are now made solvable by seemingly endless variety of numerical techniques. I hope you agree with me. So, the purpose of our lecture is to give you the flavor of such solution as applied to hypersonic inviscid flow. The roadmap for this module is given on this slide. The two different numerical methods for the solution of the exact Euler equation for inviscid hypersonic flow are discussed. The method of characteristics and the finite difference method. In reality, there is no one method of characteristics and no one finite difference method. Rather, the two primary boxes at the top of the row map represent two separate and different generic methods, for each of which there are numerous different detailed numerical approaches. As stated earlier, our purpose here is just to give you the flavor of our method as applied to hypersonic inviscid flow. Along the way, following down the left column in this slide, we will look at some method of characteristic solution. For the flow, our sharp nose two-dimensional and axisymmetric bodies at zero angle of attack and flow around axisymmetric bodies at the angle of attack as the final second part. The latter applications involve the three-dimensional method of characteristics, a rigorous challenge. Then we move to the right-hand column on this slide and consider two different finite different approaches, time marching and downstream marching. The time marching approach will be applied to the flow over a blunt body and to the interaction of an external shock wave impinging on the covered blow shock ahead of the blunt body. The downstream marching approach will be applied to sharp nose body and to the locally supersonic and hypersonic flow region over the like the space shuttle. Okay. So next subtopics, method of characteristics. In 1929 in Germany, Ludwig Prandtl and Adolf Bussmann were the first to apply the method of characteristics to a problem in supersonic flow. They utilized a graphical approach to construct the contour of a supersonic nozzle. Since then, the method of characteristic has become a classical technique for the solution of inviscid supersonic and hypersonic flow, both internal and external. Okay? Because it is classical and widely known, and because it is usually part of a basic course in compressible flow, the assumption is made that you have some familiar, I hope that one, you don't forget your previous subject, with the method of characteristics. And hence, the method will not be developed in detail here. Rather, some of the general considerations will be reviewed and some applications to hypersonic flow will be shown. So, the method of characteristics is useful when the system of governing partial differential equations is hyperbolic. And for this case, the problem is mathematically well solved by starting from an initial data surface and calculating the flow along the characteristic direction. So steady, inviscid, supersonic, and hypersonic flow is one such case. The governing Euler equations are hyperbolic, and hence, starting with an initial data surface situated downstream of the limiting characteristic, the supersonic flow can be calculated by marching downstream along the characteristic line if the flow is two-dimensional, right? Or characteristic surface if the flow is three-dimensional. Are you agree with me? Nice. So let's go on. So the governing Euler equations for two or three-dimensional steady flow, this equation we have as a d over dt, it must be equal. So exact reduced to simply differential equation in one less space dimension, called the compatibility equation along the characteristic. For two-dimensional flow, these compatibility equations become ordinary differential equations, which are more readily solved than the original partial differential equation. The solution of the compatibility equation and the evolution of the characteristic directions are in general computed simultaneously as the solution procedure marches downstream from the initial data surface. In this manner, the entire supersonic and hypersonic inviscid flow field can be calculated, namely in the exact fashion. So there is a hierarchy of solutions involving the method of characteristics. The simplest application of the method involves a steady two-dimensional and irrotational flow. This is frequently the first application encountered by the student or any listener when they first studying the method. For this application, there are two characteristics at each point in the flow, the left and right running Mach waves. Moreover, the compatibility equations that hold along these characteristics are algebraic relations. And this leads to a particularly straightforward solution of the flow. So, for a steady, axisymmetric, irrotational flow, the characteristics at each point are still the left and right running Mach waves. But the compatibility equations are now ordinary differential equations which are readily solved numerically along the characteristics. But on the other hand, for a steady two-dimensional or axisymmetric rotational flow, there are three characteristic lines to each point, the left and right running Mach waves and the streamline. The compatibility equations are appropriate ordinary differential equations that hold along these characteristics. And finally, the most complex application of the method of characteristics is the three-dimensional flow, where the characteristics are Mach surfaces and stream surfaces. And the compatibility equations are, in general, partial differential equations in two space dimensions. Okay? So For the application of the method of characteristics to external hypersonic flow, the aspect of rotationality is of primary concern. To understand this better, recall that for a given shaped body, as the supersonic or hypersonic free stream Mach number increases, the strength of the shock wave increases. If the strong shock waves have curvature, as sketched in this slide, for both slender and blunt bodies, then the entropy increases across the shock wave will be different from the streamline to the net. For example, in both figures, in left A and right B, streamline 1 here on the left and in the right has a higher entropy than a streamline 2 compared 1 and 2, both sides, because it has some through a stronger portion of the shock wave. And this is particularly acute for the blunt body in the right figure or figure B, where the bow shock is highly cut, and an intense region of large entropy gradient is produced in the nozzle region, right? Such entropy gradients occur behind curved shock waves at any supersonic Mach number. But because the shocks are stronger and usually more highly curved at hypersonic Mach number, then the entropy gradients become more severe. In turn, this introduces a large amount of rotationality into inviscid flow over hypersonic bodies, as can be quantitatively obtained from Crocco theorem written as follows. Look at here. First equation. T, yes, nabla sub S, nabla H naught minus V cross product, in we have parentheses 2 nablas with 2 cross product. Yes, inverse delta we call sometimes as a nabla. Sorry, so to note nabla and speed, otherwise it's not logical. So here we have nabla H naught must be equal 0. This is the gradient in total enthalpy at the point of the flow. So for steady adiabatic flows, and we consider this adiabatic force as H naught, in this case should be constant. And hence we have the nabla H constant equals 0. That's right. Also, here we have as cross product nabla and time speed is a classical vorticity, right? If the vorticity is finite, then the definition, the flow is rotational, right? So we have as a nabla H naught must be equal 0. And we see that an entropy gradient is nabla sub S, so directly produces vorticity on the flow, and hence making such flows rotational. For hypersonic application, these flows can be highly rotational. This is illustrated in this slide, which gives the variation of vorticity behind a parabolic Vogue shock waves as a function of the local wave angle beta. The different curves correspond to the different values of M infinity. We should be noted that first of all, the vorticity peaks at a large value in the vicinity of the sonic point at the shock. And second, the magnitude of the vorticity increases this Mach number, and you may see compared in this diagram. The point here is that any application of the method of characteristic to calculate the inviscid flow over hypersonic body should definitely utilize the rotational method of characteristic. So, historically, the first major application of the rotational method of characteristic was made by Antonio Ferri in 1946. By the way, Ferri was an ebullient Italian aerodynamicist who developed a pioneering supersonic aerodynamic laboratory in Guidonia, near the Rome during 1930s, and who was brought to the United States towards the end of the World War II to help foster research in supersonic flows at the NASA, namely in Langley Memorial Laboratory in Virginia. So, for example, Ferri's work was the basis for the characteristic calculation, as shown on this slide. To this point, in the present section, we have been reviewing some general considerations about the method of characteristics, relying somewhat upon prior familiarity with the method of the part of, and in the interest of being slightly more precise, the following is a brief outline of the application of the rotational method of characteristics to a two-dimensional or axisymmetrical external flow. So, first, the method must be started from an initial data line that lies totally within the supersonic portion of the flow and should be downstream of the limiting characteristics. The flow properties on this initial data line must be obtained from another independent calculation. The usual methods of obtaining such initial data are as follows. And first of all, if the body has a pointed nose with an attached shock wave, such as shown on the figure A on the left side, then the flow in the immediate vicinity of the node is totally supersonic, and it can be closely approximated by wedge flow in the two-dimensional case, or conical flow if we have axisymmetric case. Then, as indicated in this figure, all flow properties are known along the initial data line from the exact oblique shock solution, or from the Taylor-McCall conical solution. B, if the body has a blunt node with a detached ball shock wave, an appropriate blunt body solution must be carried out. The initial data line must be taken along or maybe downstream of the limiting characteristic, as shown on the right part on the figure B. In both preceding cases, the flow must be totally supersonic along the initial data line. And moreover, care should be taken not to use a characteristic line as the initial data line. And second, starting from the initial data line, the solution progresses by marching downstream along the characteristic line. A single element of this process, called a unit process, and illustrated on this slide. So here we have point 1 and 2, 1 and 2 are 2 points of the initial data line. All flow properties, including the streamline angles theta 1, yes, theta 1 and theta 2, yeah, are known at this point. From the known Mach numbers, and hence the known Mach angles mu1 and mu2, right? At this point, construct the left and right running Mach wave. In our case, we designated the T plus, T minus, T plus, yes, and minus, respectively, at both points as shown in this slide. Because the unit process involves only small distances in the flow, and all constructed Mach lines and streamlines are drawn as a straight line between adjacent points. Are you agree with me? Okay, so the Mach waves are characteristic lines, and hence T sub plus and C sub minus, C sub plus are appropriate designations for this line. And we should note that the C sub minus characteristic from point 1, yes, from point 1, and C sub plus from point 2, yes, intersect at point 3. We can see both, right? Thus locating this point 3 in this space. And we wish to calculate the flow properties, namely at this point 3. Okay? So assume that the streamlines through the point 3 is the angle theta 3, right? Where theta 3 is an average between the known theta 1 and theta 2. By the way, this assumption is made more accurate by iterating the unit process, as will be noted a bit more later. And trace the streamline at point 3, trace it backward until it intersects the initial data line at the next point, point 4. Okay, so next step, calculate the flow properties at point 3 by solving the compatibility equations along the characteristic line. These equations are obtained from the governing Euler equation on the left side after considerable manipulation. So, along Mach numbers, we have our first equivalence on the left upper part of this slide. Along streamline, we may say as entropy must be equal 0. So, in this upper equation, the plus and minus signs, plus and minus, yeah, correspond to the C plus and C sub minus characteristic, respectively. And J, yes, J equals 0 or 1 for two-dimensional and axisymmetric flow. So this may be for two-dimensional 0, J must be equal, and J must be equal 1 for axisymmetric flow. Okay? And next equations, ds equals 0, is simply a statement that the entropy is constant along a streamline in inviscid adiabatic flow. So a statement already contains this equation. So this equation, ds equals 0, can be replaced by two relations that depend on constant entropy along a streamline. So along streamline, we can write as a dp equals minus rho v times dv. And along streamlines, we may write the next equation too, dp proportional a squared times d rho. So both these two equations is the familiar Euler equation that holds along a streamline in a rotational flow. And it can be readily obtained by a suitable manipulation of this previous equation, along with the definition of streamline. So our last equation dp equals I squared d rho is simply based on the definition of the speed of sound. Yes, I've given you here this, remember, speed of sound, a squared this is dp over d rho under adiabatic condition, because s here is a constant along the streamline, and then any change in pressure along the streamline dp is related to a corresponding change in density along the streamline. Yes, density is a d rho. Though our relation we may rewrite in this case a squared is dp over d rho. But please note that whereas dp in all last two equations denotes a change in pressure along a streamline, dp in earlier equation denotes in change of pressure along the Mach line. Okay, returning back to our equations, we now have a system of compatibility equations which holds along the characteristic line. The integration of these equations along the characteristic can be carried out in a variety of ways. For simplicity, let us replace the differential equations and with forward differences. For example, we can equate equations written along the C minus characteristics through point 1. So we can have this on the top of the right side. So this equation written with the C plus, this with C minus, and now with C plus characteristic at point 2, we may rewrite here. So generally they're identical. What's the difference? Minus change to plus, yes, and all others are identical. Okay, so another equation that we can see here, here, around the speed of sound, written along the streamline, we may transform in this form. P3 minus P4, it will be minus rho 4 times V4, and in parentheses, V3 minus V4. And equation this one about the speed of sound, written along the streamline in next with expression with general P3 minus P4, it's A squared in point 4 times, in parentheses, P3 minus P4. Okay? So all these are equations. This is all conditions at points 1, 2, and 4. And all these conditions are known. The locations of points 3 and 4 are known too from steps 2 and 3, right? And hence, y3 must be known too. And thus, all our right equations are 4 algebraic equations that can be solved for the 4 unknowns. Which one known? P3, theta 3, yeah? V3, and rho sub 3. So now we have the slope of the C minus and C plus characteristics that based on an average theta 1, mu 1, theta 3, and mu 3, and the streamline at point 3, which is traced back using the value of theta 3 obtained in our last step. Iterate until convergence is obtained. At the completion of this iteration, point 3 is now accurately located in space. And the flow properties at point 3. Yes, I agree. They accurately obtained. So the preceding unit process is carried out from point to point in a sequential fashion, marching downstream from the initial data line. Slight modifications to the unit process are made to satisfy the boundary condition at the shock wave and the body. In this fashion, the complete inviscid flow field between the body and the shock wave can be numerically constructed. And again, emphasis is made that this is an exact solution. The compatibility of equations are obtained directly from the exact Euler equation, without any mathematical approximation or further physical simplification. And moreover, any errors introduced in the solution are numerical errors involved with the finite difference representation of the compatibility equation. In this way, the method of characteristics becomes truly exact in the limit of an infinitely fine characteristics mesh. An example of a characteristic mesh for the calculation of the rotational flow of a two-dimensional body is shown in this slide. For clarity, only the marked lines are shown here. Although keep in mind that the streamlines are also characteristic, right? And this calculation is made for a supersonic free stream with Mach, namely only 3, not hypersonic, Mach 3. At hypersonic Mach number, the shock wave would be much closer to the surface, yeah? Not so up, much closer, depending on Mach number, because the Mach angles would be smaller. The characteristic mesh would be more highly skewed. Okay? The pressure distribution behind the shock wave and along the body corresponding to the case in the left figure. In this pressure distribution, you may reflect it on the right side. But note that the pressure behind the shock is higher than along the body. And this is another example of the normal pressure gradient necessary to balance the centrifugal force along curved streamline. For the convex streamlines over the body in both left and right figures, the pressure quite naturally is going to decrease from the shock to the body, as originally discussed in conjunction with our left figure. The results shown in these both figures are included here only to illustrate the use of the rotational method of characteristics for a two-dimensional body, and to emphasize again that the method is a reasonable approach for the calculation of two-dimensional and axisymmetric inviscid hypersonic flow. You know, most practical aerodynamic problems involve three-dimensional flow. The method of characteristics can also be applied to such flow. However, the three-dimensional method of characteristics requires considerably more effort than its two-dimensional counterpart. Instead, three-dimensional rotational flow, the characteristics are surfaces, and namely Mach cone and stream surfaces. So, in general, the compatibility equations that hold along these characteristic surfaces are partial differential equations in two space dimensions. To examine these in more details, consider this figure, which illustrates a general supersonic or hypersonic three-dimensional flow field. And point B is an arbitrary point in the flow, okay? Through this point, the characteristic direction generate two sets of three-dimensional surfaces, a Mach cone with its vertex at point B and with a half angle equal to the local Mach angle M, and a stream surface through point B. The intersections of these surfaces establishes a complex three-dimensional network of grid points. And moreover, as if these were not complicated enough, the compatibility equations along arbitrary rays of the Mach cone called these big characteristics and a partial differential equation that contain cross derivatives which have to be evaluated in the directions not along the characteristics. But nevertheless, such solution can be obtained. Also, a detailed presentation of the three-dimensional method of characteristics is beyond the scope of our lecture, because it's a real scientific and research task for today. It is important to know some results obtained with this method. In particular, we will examine the calculations of Rakesh utilize a modification to the general philosophy of the three-dimensional method of characteristics, which somewhat simplifies our calculation. In this approach, which is sometimes labeled semi-characteristics of the reference plane method, the three-dimensional flow field is divided into an arbitrary number of reference planes containing the center line of the body. And this is sketched in our slide for the case of an axisymmetric body at angle beta. Figure on this slide shows a front view of the body and shock wave. Each reference plane is identified by its angular location F1, F2. Angular location F1, okay. Huh? One of these planes, say F equal F2, is projected in this figure. In this particular reference plane, a series of grid points are established along arbitrary space straight line, locally perpendicular, yes, locally perpendicular to the body surface, okay? And these grid points are not the intersections in a systematic characteristic mesh, such as shown in this slide for our two-dimensional case, okay? And rather, they are placed along arbitrary straight lines in much the same way that a finite difference grid is established. And this represents a major simplification over the general three-dimensional method of characteristics. And in this slide, assume that the flow field properties are known at the grid points denoted by solid cycles along the straight line AB. Straight line AB. And furthermore, arbitrarily choose to point 1, yeah, arbitrarily choose this point 1 on the next downstream line CD. Next line CD. Let us C sub plus and C sub minus and S denote the projection of the reference plane of the Mach cone and streamline through our point 1. Extend these characteristics upstream until they intersect the data line AB, okay, at the cross mark. Data at these cross marks obtained by interpolating between the known data and the solid circle. The preceding limited description is intended only to give the flavor of Raki's method and to set the stage for the presentation of some results which illustrating the use of the three-dimensional method of characteristics. Such results are given even in next 4 slides together with this one. In these figures, results are given for the hypersonic flow over a blunt node 15-degree cone at angle of attack. Theoretical results for the inviscid flow obtained by Rakis using the three-dimensional method of characteristics are directly compared with experimental with tunnel results. For example, this slide, namely our slide, this slide, shows the calculated and measured shock wave shape in air when we have gamma 1.4 at 3 meridional planes F. We show in the anti-clockwise direction. We have 0 degree, 90 degree, and 80 degree, 180. For an angle of attack of 10 degree at Mach equals 10. For the beam tunnel data, the Reynolds number reference to the cone base radius as base radius here, 0.6 times 10 in power 6. Agreement between the three-dimensional method of characteristics and experiment is excellent for this case. This in practice very seldom, by the way. And these figures also illustrate the effect of the nose bluntness on the shock shape. And the shock location for a sharp nose cone at 15-degree angle of attack is shown as a dashed line at the right of this slide. But note that nose bluntness displaces a leeward portion of the shock, in case when we have F equal 0 degree outward, whereas the inward portion, when we have 180, is not noticeably displaced. The calculated variations of the shock wave angle B with axial distance x is shown in this slide. It is well known that shock waves around the blunted cone at 0 angle of attack exhibit a local minimum in the wave angle, and that is as the strong wall shock wave progress from the normal shock at the nose to the weaker shock downstream. And B first decreases, right? Reaches at local minimum and then increases, finally approaching the sharp cone result far downstream. For the conditions shown in this diagram, this 0 angle of attack can result in the local minimum B occurring at conditions when x over Rn equals 10, as shown namely in this slide by the dashed line, yeah, dashed lines. Labeled as this dashed line labeled as alpha equals 0. For the angle of attack case, the method of characteristic results indicate a similar trend, except with the minimum B occurring at different axial locations, as shown by the solid lines in this diagram. But you should be noted that the wave angles for the blunted cone eventually approach the sharp cone result, as at large distances downstream of node, as seen on this right side. Yes, with the long distances, you can see this surface pressure distributions are shown in this diagram. Again, excellent agreement is obtained between the three-dimensional method of characteristics and experiment. In analogy with the shock angle, note that the pressure goes through a local minimum, which is illustrated in this figure. In expanding over the blunt node, the pressure overexpands downstream of the shoulder, falling below the sharp cone result, and then recompress to the sharp cone result far down. Okay? And this next figure shows the variation of pitot pressure in the flow field, namely along lines locally perpendicular to the body and extending from the body to the shock wave. A comparison with experiment of detailed flow field information throughout the shock layer, as opposed to just along the body surface, is always a good test of any flow field theory. So in this diagram, the comparison between the wind tunnel data and the method of characteristics calculations is quite good. For the leeward section of the flow field equal 0 degree. Some lack of agreement between theory and experiment occur near the body surface. And this is because of the thick viscous boundary layer on the leeward side, which is not taken into account by the inviscid theory. On the windward section, when we have 180 degrees, the strong variation of pitot pressure within the entropy layer is very apparent. Pitot pressure reaches a peak just outside the entropy layer and then decreases towards the shock wave. And this is because outside the entropy layer and boundary layer on the surface, the local supersonic Mach number increases towards the shock wave, and hence resulting in progressively lower pitot through tube, lower pituitary pressure. Okay? And finally, to emphasize the three-dimensional nature of this flow field, this slide illustrates the circumferential surface pressure distribution around the blunt cone at angle theta. Unlike the previous data, this slide pertains to hypersonic flow at helium. Helium has a only different gamma number, 1.667. At Mach number near 15, 14.9. Once again, excellent agreement between experiment and the three-dimensional method of characteristics here is obtained. And we have seen that the method of characteristics is a viable approach toward exact solution of such flow, and indeed has been used extensively for such cases, especially in the time period before 1970. However, the method of characteristics is sometimes tedious to set up and program. In the days before high-speed digital computers, the method of characteristics at that time was carried out by hand calculation. Yeah, the ultimate interiors by your even non-programming calculator. And for this reason, in more recent times, simpler finite difference solutions have supplanted the method of characteristics in many, many applications. I hope you enjoyed this lecture, and I'm looking forward to seeing you next time to continue this lecture topic. Bye.